Intro. In this experiment, I analyzed and modeled the motion of a star orbiting a black hole to find the net force on the star for all the data points using Newton's second law and the parallel and perpendicular components of force. In addition, I estimated the unknown mass of the black hole. Assumptions. The star has a mass of 2e30 kilograms. The net force on the star is solely due to the black hole's gravitational force. Time between the data points in the trajectory is 1 day. The black hole is located at the origin. Initializations and edits made for the code. I edited the template code to solve for the parallel and perpendicular components of force. I approximated derivatives such as dp over dt using the difference between the final and initial values, since there is a lack of uncertainties in the model. In the while loop, to find the parallel component, which accounts for the star's change in speed, I use the formula dp over dt times p hat. As for the perpendicular component, which measures the curving motion, since both components are equal to the total dp over dt, I use dp over dt minus dp over dt parallel. I made the arrow scale small so it could be visible in the model. As shown when the code is run, the vectors for the gravitational force and its components increase when the star is closer to the black hole. So now I'll show you how my code looks like and what it models. So this is my code right here. This is what I initialized. The while loop is right here. Both components. And this is it when I run it, modeling the orbit of the planet. All right. Calculating the mass of the black hole. To solve for the mass of the black hole, I use the formula for the magnitude of the gravitational force, Fgrav is equal to g/mm over r squared, and converted to m is equal to the magnitude of the gravitational force times r squared divided by g times m, and put it in my code to get a mass of 6.33 e to the positive 33 kilograms, as shown here. What does it mean? Although Newton's second law states that F net is equal to dp over dt, the rate of change of the momentum, the two are different in that dp over dt can be visually observed and measured, whereas net force can't be seen, but rather is a result of motion. What if? If the current black hole was replaced with one with a different mass, it wouldn't be possible to tell the difference. This is because the mass of the black hole affects the magnitude of the gravitational force, whose perpendicular component affects the direction, and whose parallel component that affects the magnitude of the star's motion, which is supposed to remain unchanged. Part 2. Don't crash. I use the gravitational force equation to calculate the net force for the planet and for the ship. I also use Newton's second law and the position update formula to update the speed and position of the planet and the ship, so the movement is modeled within my code. To find the initial velocity for the spaceship to get close enough to the black hole without crashing, I pretty much just did trial and error until I got the results shown in my model. The ship ended up being around 9.7 e to 10 meters away from the black hole. And I'll show it now here with my the second part of my code. So this is where I initialized the this part of the code, and this is a while loop. This is where I inputted the forces on the planet and on the ship, and this is where I update their positions and their velocities. This is how it looks like. And so as you can see, it doesn't crash into the black hole. So that's good. Yeah, that's all. Thank you.